So I'm pleased to welcome Jake Carstens. Jake is an assistant professor in the Department of Atmospheric Sciences at University of North Dakota, a position he began in 2024. Before arriving at UND, he earned his BS, MS, and PhD from Florida State University, and then worked for 2 years as a postdoctoral scholar at Penn State. His main research emphasis is tropical weather and climate, including convective organization, tropical cyclogenesis, and tropical cyclone structure and hazards in the future climate. He's also interested in weather and climate communication, with growing involvement in social science research, atmospheric science education research, and broadcast meteorology. Jake teaches courses in weather forecasting, broadcast meteorology, tropical meteorology, and numerical weather prediction at UND. He's active in community and professional service, including as faculty advisor for the UND Weather Update Student Broadcasting Organization and the chair-elect of the AMS Board for Early Career Professionals, among other roles. Welcome.
All right, thanks, Hugh, and thanks to everybody for the warm welcome here. I kind of weaseled my way into doing a seminar, honestly, by running into Gretchen at the AMS Mesoscale conference back in June and basically saying, hey, I'll be in Boulder for this NOAA UFS workshop. Can I just visit? I've never been to Boulder before, much less NCAR, and here we are. So never be afraid to network is the lesson from that, as my early career board experience has dictated. So thanks for the introduction, Hugh, and for all the great conversations I've had with many of you today. I'm looking forward to hopefully sharing a little bit more of my world with you guys over the next hour before I hit my flight back to North Dakota tonight. But so my presentation today is mostly going to focus on tropical cyclones in climate models. And this is kind of an extension of some work I did as a postdoc at Penn State with Anthony Didlake and Colin Zarzicki, funded through NOAA's Climate Program Office. I'll start by just kind of introducing myself to those of you that I haven't met yet. So obviously a lot of this was already covered by Hugh's introduction. I did my PhD research with Allie Wing at Florida State, so I was her very first grad student. And honestly, this seminar is a nice kick in the pants for me to really get my foot back on the gas research-wise with all the teaching responsibilities I've been juggling over the past year or so in the new faculty role. So I'm happy to kind of chat about any of this other stuff that I'm up to. I'm pretty active in the AMS community as well. So to outline this presentation, I kind of want to start with a little bit of background motivation because, of course, the irony of a guy showing climate model data at a mesoscale and microscale meteorology lab is something that I probably shouldn't ignore. So I'm going to at least talk about that. Share what I'll consider the proof of concept for the larger project that our group is pursuing, using aerifive reanalysis to analyze asymmetric structure of tropical cyclones. This is based off a paper I published last year in the Journal of Climate. And then moving forward and kind of taking off the training wheels. When we don't have observations to assimilate into a reanalysis product, right? We have a free-running climate model. Are we able to actually capture these mesoscale features of how vertical wind shear affects a tropical cyclone, both its intensity, its structure, its distribution of hazards? So this is a manuscript that I'm working on, have been working on for a little while. And then kind of looking into the future, I talked, and I know in my abstract a little bit about the high-res MIP and mesoclip ensembles, and I'll share some very, very preliminary results from one of those, at least looking at the kind of distribution of the vertical wind shear that's affecting tropical cyclones in these simulations, kind of moving beyond the ways that we look at TC environments from a climate perspective, from these kind of monthly mean parameters or these genesis potential indices, these different kind of composite metrics, to really look at the synoptic environments unique to each individual tropical cyclone that exists in a model. And then I'm going to finish by actually just showing off some teasers as a new faculty. Pretty proud of what my students have been up to over the last year or so. So I'll show some of the other projects I'm up to because I'm really starting to dip my toes in other parts of the tropical cyclone world a little bit. So starting off with the very basic motivation, right? The whole tropical cyclone climate relationship. The very easy part of this, or the very intuitive conclusion, I guess, that the community's kind of come to is that a warmer world provides more fuel for tropical cyclones that do form. And I say the tropical cyclones that do form because, of course, there are a lot of questions about TC frequency, both observed and in the future climate. With the past, we're looking at changes in our observing system, the quality of observations that we have, even just subjectivity from basin to basin in terms of how we classify tropical cyclones. But going forward, too, there's a lot of questions, right? Even if the atmosphere is warmer, right, and more, I guess, energetic, that doesn't necessarily mean that we're going to have the same or, the same kind of pathways to tropical cyclogenesis that we see in current times. So This is a map from the fantastic Knudsen et al. 2020 synthesis paper. There's been a couple of updated publications since then looking further into the TC climate relationship that I encourage you to check out. But we're pretty confident about increased projections of tropical cyclone rain rate. There's some nuance to it in terms of the spatial distribution, inner core versus rain band precip, how this particularly scales with Clausius-Clapeyron thermodynamic expectation. But frequency, much less confident. If you look at kind of a mashup of all the climate model runs, I think the consensus is a slight decrease, but there's a lot of variability, including the way that we actually model tropical cyclones, like some of the statistical downscaling techniques producing a much more robustly large number of TCs in the future climate, for example. I'm interested for this talk in the intensity part because, again, right, warmer oceans, more ocean heat content, a lot of the core ingredients that you expect to strengthen a tropical cyclone that are there. But these projections are maybe not as pronounced as you might think, right? There's some nuance to it. We generally expect increases in the proportion of tropical cyclones that become major hurricanes, category 3, 4, 5 storms, and a modest increase in the mean intensity is generally projected, but it's maybe not as substantial as one might expect. And where my group wants to address this is through looking into vertical wind shear. So we know in reality that asymmetric tropical cyclone structure is very common, and it's very important for how we predict TC evolution operationally and how hazards are distributed. I always like to use this GIF of Hurricane Sally as the reference point. Of course, it's a little bit biased because of where the radar site is in this case, but it's a pretty, I think, prominent example and maybe a little bit underrated of sorts of one of these tropical cyclones that rapidly intensified in what we might consider a marginal environment, one where, we had questions about the favorability, at least in terms of the dynamics of the environment for it to strengthen. There's been a lot of really outstanding work done over the last 3 decades and even outstanding synthesis articles written over the past couple of years by people in this room about vertical wind shear and how it affects tropical cyclone structure. It induces asymmetry in vertical motion, thermodynamic fields, inflow, outflow, essentially kind of a disruption of thermal imbalance that causes this anomalous inflow and rising motion in the so-called down shear section of the storm. It all kind of starts with the tilt of this otherwise upright vorticity column. And it leads in observations, this is some tail Doppler radar precipitation measurements or reflectivity measurements from a paper by Paul Reiser. Convections favor down shear. In general. It's, of course, not all storms behave the same way, but we tend to see this rather systematic wave number 1 asymmetry, where the contours here indicate vertical velocity in the mid-levels, and the shading here indicates radar reflectivity. So you kind of see this little kind of downwind shift in where the heaviest precip is falling, as you might expect, right? When you're in the eye wall of a hurricane, those hydrometeors are being affected pretty substantially. And so, obviously, all of this is very mesoscale. And what I'm going to show here is arguably even more mesoscale, right? Looking at ventilation and how vertical wind shear tilts a tropical cyclone vortex. This is a really awesome, actually 2-part paper from Josh Allen when he was doing his PhD work at Albany. And this is a map of radial ventilation in a few mesoscale simulations. And so what I mean by radial ventilation is essentially the import of low theta E air into the core, into the circulation of the tropical cyclone by either radial inflow or by downdrafts that bring that air and kind of flush it down into the boundary layer. So there's a few different simulations here that vary in terms of the environmental humidity imposed, in terms of the magnitude of the vertical wind shear. One of the things I want to indicate to you first is just these gray X's on these plots, again, showing the location of the mid-level center relative to the surface pressure minimum, right? So there is this tilt of the vortex that does take place in observations and mesoscale models all over the place. We know it's a thing. We see it all the time. It's one of the things that we're really interested in for forecasting near-term intensity evolution. But again, the idea of this is kind of the red shading on this plot. These are regions where you're importing low theta E air anomalously through radial inflow into the core of the storm. At this case, it's at a height of 5 kilometers, but we can analyze this throughout the depth of the troposphere and find a lot of variability. And so this kind of gives me the question from the climate perspective of, does vertical wind shear somehow offset the effect of the warming oceans, the thermodynamic ingredients you might expect to increase TC intensity, to somehow offset that, at least for some storms, right? Has the effect of vertical wind shear on a tropical cyclone different in the future than it is now, for example? And can we even model this from a climate perspective? That's kind of where my work is, I think, mostly focused. So I want to address that question of, do global climate models even stand a chance? Because I'm talking, of course, to a room of mesoscale modelers who really know their stuff in that sense. And there's a big argument for no, right? This is a paper from 2019 by my old PhD advisor, just comparing lifetime maximum intensity from a bunch of different climate models to what we see in observations. And as you might expect for such coarse data sets, you're having a hard time resolving important inner core processes. A lot of times you can't resolve an I at all in a tropical cyclone in a climate model, right? So of course, there's issues with reproducing the observed climatology that we have. And there's also inconsistency in structure. This is a bit more of an involved plot, but it's basically a 6-part imagery of warm core and vertical motion composites for storms with similar intensities. This is from Yumin Moon's work back in 2020, and he had a fantastic follow-up article in 2022 that I'll mention on the next slide. One of the important things here is the kind of, first of all, the differences that different climate models have and kind of how they produce, warm core structure through the depth of the troposphere and relative to the surrounding environment. But I think more importantly, if you look really closely at the contours, there's rising motion in the middle. They're not really resolving the actual eye dynamics, as effectively as they should be, certainly. And in general, of course, we're in a world of modeling where we have a lot of sensitivity to resolution, physical parameterizations, dynamical core. Collins Orzycki even published a paper about changing the time step and how that completely changes TC frequency in a GCM. But I think there's an argument for yes as well to at least explore in the rest of this talk. Number one here, this is a climate model, so that's really cool. I'm honestly just getting involved or starting to get acclimated to the mesoclip simulations, these really high-resolution CESM coupled runs, looking at climate from pre-industrial all the way through 2100. And this is the ocean in particular, so the atmosphere is a little bit coarser. But we are starting to get to, of course, we're still in the space where we have to parameterize convection and all of these other relevant physical processes, but we're starting to at least move toward more of what the operational models are spitting out at us, right? And so I have a new master's student that's just about to get started on working with tropical cyclone data in mesoclip, and I just had a great conversation today with one of you about some kind of ideas for that going forward. So, of course, as computing power improves, we have that going for us. But also there is some evidence, this is Yumin Moon's 2022 paper, that modern GCMs can at least capture, maybe qualitatively, I guess I can say, the vortex tilt and the asymmetry in rainfall that we do see in observations. So this is a map where the shear vector is pointing upward, 8 different climate models just looking at the distribution of rain rates. And you kind of see this well-defined maximum of precipitation in the down shear left portion of the storm, just like we saw with the reflectivity imagery earlier. So there's evidence that at least some of this relationship, sure, we're not going to be able to capture a mini supercell in a rain band explicitly, there's no way, but the kind of storm scale asymmetries, this sort of wave number 1 way that we think of things, and therefore maybe the ventilation, some of the other effects that shear has on a tropical cyclone could be worth exploring in this context with data sets that we already have available to us. Because of course you could explore this more with, thermodynamic global warming simulations or, some dynamical downscaling approaches as well. So as the proof of concept here, I published a paper last year, and there's the QR code for it, looking at tropical cyclone asymmetry in ERA 5 and also CFSR reanalysis, but I'm just going to show ERA 5 today. We can kind of think of it for this talk as sort of a climate model getting its hand held a lot along the way, right, by having observational data assimilated into it. So we know that there is some reality that this data set is trying to produce for us, right? But we can still, because we have a lot of the same kind of physical process parameterizations that you see in a free-running GCM, we can still, I think, start with that question of how realistic is storm structure. This particular map is actually showing CFSR tracks, but I'm mostly just doing it because I needed a pretty GIF in here. So we track tropical cyclones over a 10-year period using tempest extremes. Some of you are probably familiar with this, but I will go over the idea generally. I'm not going to specify the specific thresholds in this talk, but I'm always happy to share that with you if you're interested. We first look for a local pressure minimum, as you might expect. But we co-locate that specifically with a geopotential thickness maximum within a certain radius from this pressure minimum, because we want to identify a warm core cyclone instead of something extratropical. And for the sake of filtering out some kind of irrelevant noise, we ensure that the feature persists for at least 2.5 days before we consider it a TC and we stitch that track together. So this is an example of tracks from 2012 in CFSR, and you'll actually be able to see, if I let this play out a little bit longer, you'll see Hurricane Isaac being reproduced as it made landfall in Louisiana eventually. So, and even here, we're seeing, I haven't put the color scale on here, but the red indicates TCs with hurricane force winds. So a reanalysis product actually able to put that out is pretty encouraging. Anyways, I'll go really quick into how we classify tropical cyclones, because we are doing this from a composite approach, at least for this portion of the talk. I've tried to start doing some work looking at the evolution of individual cyclones subject to shear and see kind of how their intensity and their structure evolves and how realistic that process is. I'll also note really quick that I'm only considering cyclones that are equatorward of 30 degrees. It's kind of a simple cop-out way to limit cases of extratropical transition instead of applying some sort of jet stream related filter. So I composite by pressure and vertical wind shear magnitude. And as some of you in the room might know, right, shear is not as straightforward as it might seem. In reality, how that shear is distributed through the layer can really make a difference for how an individual cyclone evolves. But for the purposes of this talk, we're going to basically take the parameters you see in SHIPS, the kind of operational statistical hurricane intensity prediction model. So I calculate shear with two different approaches here, and the results for the sake of this paper were essentially the same. So I'm only going to show you the bottom one here. But to kind of isolate the environmental flow from from the shear associated with the TC, because it's this weakening kind of transitioning to an anticyclone system as you move up through the atmosphere. The two strategies that get used are to simply average winds at two different vertical levels in a 200 to 800 kilometer ring, this kind of green ring that I have here. But the more popular technique, I would think, and I do believe this is actually a little bit better correlated with intensity, is to remove the vortex flow first by subtracting the irrotational and non-divergent winds, and then averaging the winds in a 0 to 500 kilometer ring. Pressure, I'm just going to use a simple pressure scale that Klotzbach et al. 2020 initially developed, and this was adapted by a more recent paper to include weaker cyclones. So using pressure, because it's better simulated than maximum wind in climate models, it's a little bit less sensitive to resolution and other issues, and it's better correlated with observed damage statistics, as some of Phil's work has shown. So that's kind of the approach I'm going to be using here. And consider this next slide the orientation. I'm going to spend a lot of time on this because there's obviously a lot happening, and because this kind of figure is pretty ubiquitous throughout the rest of my talk. And so what you're seeing here is kind of a depiction of the low-level shear relative kinematics. On each of these plots, and I'll go through the whole left to right evolution in a minute here, the wind shear vector is pointing upward. Everything is in a shear relative coordinate system. So I have a little map up here in the top left to indicate what the different quadrants are, if you're less familiar with that kind of terminology. The shading here represents tangential and radial winds at 900 millibars, so about a kilometer or so above the surface. And the contours are showing where you have ascent at 850 hectopascals. As I move from left to right here, all of these cyclones are averaged, or they have similar pressures. They're in the range of 975 to 990 hectopascals, just to kind of, keep that similar, because as you might expect, a stronger cyclone might be a little bit more resistant to a shear and vice versa. And as we move from left to right, these are basically environments of increasing shear. So I kind of simply divide things into three bins: low shear, where it's less than 5 meters per second, moderate, 5 to 10, and strong shear, 10 meters per second or above. It's pretty close to the observed climatology of wind shear, at least for North Atlantic tropical cyclones. And so what you're seeing on here is kind of what you would hope to see, at least from my perspective, where as you strengthen the shear, you see more of an asymmetric response in both the spinning part of the circulation and the inflowing, overturning part of the circulation, right? We have, under low shear, a relatively symmetric cyclonic circulation. We also have non-negligible rising motion taking place throughout the entirety of the kind of inner core of the storm. But as we crank up the shear, we see much more of a kind of wave number 1 asymmetry in terms of both the tangential wind, the radial wind, and the vertical motion. Right? We kind of see these contours really starting to pack and focus directly down shear. We're starting to see even a little bit of asymmetry in terms of the extent to which appreciable rising motion takes place. Of course, we're seeing a really strong dipole where we have strong low-level inflow down shear that's compensated by outflow up shear. We also see evidence of kind of the dynamical response you might hope for when you have really strong inflowing converging air, where you have a spin up of the tangential wind immediately downwind of that. So there's a lot of things going on at once here, but I wanted to kind of show this for like 5 minutes at a time, because this is, I think, kind of setting the stage for the rest of the analysis I'll be sharing here. I want to blow up a plot really quick just to show an example of precipitation asymmetry as well. And I'll say with this paper, I've gone into, frankly, a lot more gory detail than I'm going to share today, looking at kind of how the convective and large-scale cloud parameterizations treat rainfall separately, how this relates to environmental conditions like instability and convergence. I've even done a whole bunch of 3D mapping looking at cloud, liquid, and ice, and how that's simulated in this reanalysis. I'm kind of showing you the basics for the sake of this talk. So here is just looking at total rain rate. It's for a particular composite, which I'm going to call category 1 moderate shear. An example of, right, one of these kind of marginal cases where you might expect a storm to strengthen or you might expect it to weaken, right? There's a lot of variability, not a lot of predictability. And so the shading here is just rain rate. The black contours in this case are representing mid-level ascent. So that's why they're kind of extending farther outward as opposed to being just above the boundary layer. And so just to kind of list out some of those results I already sort of alluded to, and again, this is all, and in the paper, I've actually gone and compared this with reconnaissance radar observations. So there's a little bit of a, kind of apples to apples comparison to do there. But we see all the things we kind of hope and expect to see. Strongest descent is forced directly down shear within about maybe 150 kilometers or so of the center. The heaviest precipitation is focused in the down shear left quadrant where my cursor is. I guess it kind of blends in with the heavy rain. If we look at this outermost black contour, we're again seeing what could be evidence of enhanced rain band activity, where we have kind of a more wide-reaching area of appreciable rising motion. And then this is kind of not shown in this particular image, but we do see evidence both in terms of the thermodynamics and the kind of kinematic response for more of a transition to a stratiform rain mode that takes place left of shear as you're starting to kind of decay and rain out, at least in the eye wall, or eye wall, I guess you could say in air quotes. Another thing that comes up, and again, it's not really shown directly in this figure, but we kind of see this sort of recharge-discharge cycle that we'd see in real shear tropical cyclones as well, where boundary layer moisture gets depleted as you kind of go through this rain-out process. But at the same time, if you recall from the last slide, and I'll just pull that up really quick, remember, we have really strong tangential flow taking place left of shear. And so with that, we're able to kind of kick up our surface fluxes and sort of recharge what's going on in the boundary layer to eventually kickstart new deep convection as we start to move back around the circulation. So again, we also consider how rainfall is partitioned between convective, large-scale cloud parameterizations. It's frankly a little bit gory. There's some figures in there that I kind of regret making in hindsight because they're very busy. But I want to kind of move on to a free-running climate model and ask the question of what happens when we take off the training wheels and we don't have any observations to assimilate directly to force things toward reality, to force Hurricane Helene to actually happen in our model, right? So I'm going to use a few Cam 5 simulations for this part of the talk, and this is a manuscript that I'm working on right now. These have been used in the past to look at several different things, including the kind of distribution of precipitation in inland landfalling tropical cyclones, to look at how simulating easterly waves over Africa, like once they're still over land, how that translates to TC climatology. So there's a lot of utility these simulations have brought out for us over the years as a community. I'm just going to focus on the North Atlantic, but one of the things that I am interested in for this larger analysis is the resolution question, right? This is a variable resolution grid. We got about a 1/4 degree grid spacing in the North Atlantic and 1 degree elsewhere around the world. So if we're talking about the computational efficiency versus actually capturing the details part of things, that's an important question to think about. So I have done some analysis looking at storm structure in the West Pacific as kind of an example of what's going on in this 1 degree grid. But I'm also interested in the climate side. If we look up, if we kind of take a look at what's going to happen, by end of century under a few different scenarios. So I'm not just going to consider 8.5 here. I'm going to also introduce the kind of moderate 4.5 tier for radiative forcing and therefore warming. And when I'm looking at the mesoclip ensemble, which I really only dug up a couple months ago on NCAR's Research Data Archive, which I guess has a new name as of like 2 days ago, there's a lot of fun stuff for me to kind of dig into with that. So I'm just going to overview the asymmetric TC structure in Chem 5 first before starting to go into a little bit more of the weeds about what the structure of these storms might look like in a warmer atmosphere. So the figure on the right side, I'll get around to that in a sec, but that's kind of more similar to what you've seen already with ERA 5. I want to focus real quick on what's going on the left, because this is a new kind of plot that I haven't shown you guys today. This is actually looking at relative humidity average in the mid-troposphere, which I'm going to take broadly to mean 700 to 300 millibars. And I'm actually plotting the azimuthal range of relative humidity. So I'm basically saying if you go around a circle at a given radius, by how much does that RH vary? It's a measure of wave number 1 asymmetry, essentially. And so that's the question I'm basically asking here. I want to phrase this as simple science questions we can interpret in 30 seconds, right? And so when you look at this, it's a function of radius here. So the farther we go out from the storm, as you might expect, there's a little bit more variability in relative humidity. There is a non-negligible variability, which, if we're looking at how a shear relative asymmetry can be reproduced in a climate model, that's encouraging for us, even at relatively small radii. And I think the thing that's better is the fact that we see with the thickening blue lines here, this very robust increase in the wave number 1 asymmetry as we crank up that shear. And again, this even takes place at radii like 100 kilometers or so. So of course, in the environment, you might capture that regardless, but to have this happen close to what we would consider the inner core or the eye wall is something that is encouraging for me at least. And this is looking at 850 millibar vertical velocity. So similar to something I already showed with ERA 5, is ERA ascending uniformly throughout the TC, right? Simple questions that we can kind of answer to start off. And we see this signal where this is omega, so the darker colors are actually ascent, where it's negative. So again, the signal of inner core convection being most prevalent in the downshear left quadrant. And then also this little area over here where the yellows are just a little darker, suggesting there could be some more enhanced rain band activity or at least more frequent precipitation events taking place in this sector of the storm at outer radii, which is what we see in reality. So some other questions that I'm going to address over the next couple of minutes here on TCs in the historical climate. I'm just going to focus on one particular composite. Again, what I'll consider to be category 1 moderate shear for simplicity. And again, how does the TC circulation respond to shear? This is just looking again at the radial wind, just near the top of the boundary layer, about 900 hectopascals. And of course, we see the signal that we just saw in ERA 5, where we have very strongly focused inflow, convergence, deep convection that's focused in the downshear sector of the storm. So we're still seeing that even in a quote-unquote moderately sheared environment, depending on your definition. Tangential flow, again, looking at the cyclonic wind pattern, we see that same signal we saw in ERA 5, where we have this strong converging flow, this angular momentum convergence that takes place, and corresponding spin-up of the cyclonic flow immediately downwind of that. But I also wanted to start looking a little bit, because I've only shown you mean structures across a composite of many cyclones. I want to also look at a little bit of the variability within the composite. So this is just a heat map of where the heaviest rain takes place. Pretty straightforward. And you're still seeing the signal very strongly of the rain being forced most often in the down shear left quadrant. So in terms of both the kind of magnitude and the variability of the signal, we're seeing everything that we theoretically would want to see, at least for the historical climate. So again, we can't simulate many supercells in a rain band, right? Like we can't use this stuff to look, I mean, we can look at tornadic environments, I guess, but we can't look at individual, like updraft swaths or anything like that. So, but Cam 5 is capturing how shear should tilt to TC, and I do actually have some. I should dig those up maybe if you all have questions afterward. But I do have some plots looking at the actual vortex tilt itself, which is overestimated but directionally correct, and the response to that tilt. So this is getting into what I'm going to consider the more exploratory part of the talk now. I'm actually just about 3/4 of the way done here, so I should be good on time. So all of the stuff I'm going to share the rest of the way is not stuff I have all the answers to yet. And this is why I come here for these kinds of conversations. So the next couple slides are all about the future climate perspectives. And so what you're seeing here is actually a difference plot. And if I forget if James had shown these plots when he gave his seminar here in May, but it's very similar to some of the work he's been doing with a different model. I'm asking here if TC rainfall disproportionately worsens in a specific sector of the storm. So the green colors here indicate where you have more rainfall, or heavier rain, I guess I should say, falling in the warming simulation relative to the historical climate. And the brown is indicating where you're having less rainfall in that particular shear relative grid point, we'll call it. And I'll be honest, this is a little bit cherry-picked. There's not as systematic of a signal as I necessarily would have expected just from looking at this individual figure. But this is one example where the most amplified rain rates are taking place in the part of the storm where the rain is already the heaviest, which hazard-wise, of course, is going to have important implications, but also I think should have some downstream impacts on intensity trends for these individual simulated storms. So these kind of analyses are things I'm really trying to better constrain and kind of figure out the why behind them. And this one's a lot, so I'm going to take my time going through this. My undergrad research was in integrated kinetic energy, and I always thought it was a fascinating concept because it took all these metrics like ACE and Saffir-Simpson, Vmax, and kind of brought another wrinkle to it, accounting for storm size in a simple way. So I always kind of had a fondness for Ike. I always liked Ike, right? And so this plot is actually looking at asymmetry in the TC wind field. So for reference, by the way, Ike is just the accumulated kinetic energy, essentially. In the way I'm defining it is actually just within a fixed 500 kilometer ring. But the way we do it operationally is usually using the radius of tropical storm force winds. So it's basically taking all the kinetic energy of the wind field within some given radius. So it accounts for, again, the Vmax and the storm size. And so I'm able to split this up into different shear relative quadrants, look at the azimuthal mean of the Ike, look at how that compares, and I have the West Pacific in here, which again is on a coarser grid, just to throw it all kind of at you guys at once. But we do see, just to kind of make things a little bit more straightforward, a systematic ranking of how the different shear relative quadrants behave in terms of, again, there's a ton of variability in here, right? And that's something that, frankly, I'm still kind of working to parse through. But there is this kind of systematic ranking where the down shear left is, I guess you can consider the most energetic quadrant out of the four in terms of its wind field, and moving back down to the up shear right. I also notice a slight increase in median Ike. These, again, box plots have a lot going on. These differences may not be statistically significant, and there's actually a paper published in 2021 looking at Ike in climate model ensembles that suggests that, no, it's not significantly increasing in the future. But I really want to break down the kind of structural morphology of the wind field because I do think that has a lot of relevance for how a storm might be able to resist a shear, for example. And so this is kind of getting into the ventilation part of the work, and this is, again, very exploratory, but I think it's kind of cool to do ventilation in a climate model, honestly, so I'm going to show it. Right, so I already kind of explained what ventilation was toward the beginning, but again, it's cooler or drier, low theta E, environmental air being imported into the circulation through either downdrafts or inflow. There's been a lot of work done over the last 10 years looking into this, and some work now starting to do with observations. So this is what downdraft ventilation looks like in one particular climate model example. So this is the moderate warming simulation, RCP 4.5, looking at downdrafts at 850 millibars. And so we can actually see, if we connect back to what we talked about earlier, that there is kind of evidence for a transition to more of a stratiform rain-dominated regime in the left of shear section of the storm, which, again, we see most often in reality. Not every storm behaves the same way. But we do see this signal where cooler and drier air is being imported into the boundary layer over here. But the thing I'm really interested in is kind of looking at how this compares between the future and the historical climate. And again, this is just one example. I really need to analyze this more to figure out anything systematic, but I do think this one's at least thought-provoking, where if I'm taking a difference between the warming run and the historical run, I see this signal right here, up shear, where there is stronger radial ventilation of low theta E environmental air taking place. And so what that would, the question that would kind of pose is, does this limit TC intensification in the future climate, for example? Again, one example. This is not exhaustive by any means. A lot of these analyses look very different. And kind of where I actually want to take this is to motivate it into some of the work that I'm just now starting to do with my group at UND. So a lot of this was actually postdoc work, and then I taught 3 classes. And here we are now. So the rest of the talk here, I'm almost done. I'm just going to share some new work I've been up to with the high-res MIP ensemble. I have 14 simulations that I spent a long time, longer than I'd like to admit, downloading. Including from 6 different modeling centers. And one of the questions that I am starting to address is, are GCMs capturing realistic distributions of the shear that's imparted on tropical cyclones? And so I should probably clarify why I'm asking this question, and it's because a lot of the work considering, tropical cyclones and climate, right, or WindShear in the future climate has been kind of relying on monthly means or other kind of bulk statistics or composite parameters that don't necessarily account for the synoptic environments that are unique to a given cyclone or a given disturbance. And so I'm trying. We have 6 hourly data available for all this stuff, and so we're gonna take a shot. And so there's a lot going on in this figure, and I really should have made the observational lines a little bit thicker, really stand out a little bit more. But this is a cumulative distribution of vertical wind shear. That's, again, unique to all the tropical cyclones that I've tracked in these 14 different climate models, plus ERA5, plus observations. The reason that there's solid and dashed lines is because I calculate wind shear both ways, both using that kind of just static annulus technique where I don't do anything to the wind, and using the arguably more popular technique of removing the vortex flow first. These are honestly fairly similar. And one of the things that I'm at least encouraged by initially, I haven't done a lot of work yet in terms of the actual structural, or I've looked at the intensity response to shear, but those distributions are a little bit of a nightmare right now, and I need to figure out a different way to look through them. The thing that at least encourages me is the fact that the observational distribution falls pretty much at the center of the model envelope. So there's definitely some that are kind of out to lunch in terms of how they're depicting wind shear. Another trend that doesn't really stick out from this particular plot, I really should just show one type of shear to really make this stand out more, but we do tend to see that higher resolution models, and that's one of the things about high-res MIP that's really great, is they basically take the same model and run it at multiple resolutions to better give you an idea of what resolution does to these extreme weather events. So the IPSL French model, I have 4 different simulations of that available to me, thanks to Stella Borden. And generally, cranking up the resolution results in kind of rightward shift of that distribution. Stronger shears on average imparted on TCs. But some of that might also just be the fact that the TCs themselves are stronger, right? And so when you're just calculating, when you're calculating wind shear from a fixed area without actually manipulating the wind field, there's of course going to be potential for some kind of signal there. And so I'm going to do some kind of take-home messages here. I'll revisit the slide at the very, very end just so we can actually it's not a total left turn, but I do want to show some of the other stuff I'm up to before I finish. So again, a climate modeler comes into a microscale meteorology lab and asks, does shear offset the effects of a warmer atmosphere and ocean on TC intensity? I'm kind of using climate models, or at least the data that we already have available to us, right? That's one of the things I really try to stress in my own work, at least with the group that I'm working with at UND, where frankly we don't have fancy supercomputers to run right now, is there's a lot of value we can get out of existing data sets. And so that's kind of the core question I'm addressing with my group, and I'll shout out my other grad student, Mark McGarry, who actually visited NCAR, visited this lab a few months back, as well as Kelly Thrower, who's a senior doing a project with me as well, considering grad schools, so if you know anybody, Kelly's great. We've shown, I think, that high-res climate models can, at least qualitatively, capture how vertical shear tilts at TC, and the structural response to that tilt. We see some evidence. Again, it's not as systematic as maybe I would like for publishing in Nature or something, but evidence that rainfall might worsen where the TCs already rain the most heavily. Or at least those are the kind of questions I'm interested in exploring further. We project slight increases in integrated kinetic energy, so the kind of full wind field of a tropical cyclone with warming. But really the big thing, I think, as I go into this year now, with a research group kind of fully up and running now, is that these diagnostics can be and are being applied to a much larger suite of climate models. So I'll come back to this slide at the very, very end, but I just want to finish with a couple of other projects I'm up to that are a little bit less climate model-y and also in the tropical cyclone world, but really trying some new things. So I talked about this with Quentin earlier, so I saw you nodding. One of the things that I actually am doing on my startup is actually re-exploring that Ike concept that I worked in back in my undergrad research. I joked with Quentin this morning that I kind of abandoned it because I didn't have any talent, and that was kind of true. As a senior, I didn't really know what I was doing, and I didn't really understand the kind of broader process of research as well as I maybe could have at that time. So now I kind of have a mulligan, and I have a really motivated grad student, Sydney Walters, and actually another undergrad who just joined the group today, to use synthetic aperture radar and downscaled ASCAT, scatterometer observations, to basically look at the structural morphology of the tropical cyclone's wind field. So Sydney's made both these plots, and this is just SAR images of Hurricane Lee from 2023. This has kind of been the case study she's been working with most predominantly, since there's plenty of good overpasses from the SAR instrumentation. So on the right, it's just radial profiles of wind speed near the surface, but done so in shear relative quadrants, which I believe is I don't think those are available through any of the public forums. And so what we're doing is trying to reconstruct Ike using these very high resolution obs, but also looking at the kind of spatial structure of Ike. Is a more up shear skewed distribution of tropical cyclone winds. Does that somehow make the storm more able to resist shear or negative influences aloft, I guess you could say more broadly? These are the kind of questions that I'm starting to explore, and it's been a nice way to kind of get into satellite meteorology for the first time in my career. Another thing that I'm working on is I'm still kind of in touch with my old group at Florida State. Actually need to submit a grant to my university tonight as I'm sitting in the airport. But we're using in situ and satellite observations to look at the interplay between radiation and ventilation. I've already talked about ventilation extensively in this talk, but radiative feedbacks on tropical cyclones, essentially driven by spatial gradients in mostly long wave radiative heating, have gotten a lot of renewed attention over the past decade or so in the community. And it's interesting, I think there's a paradox here that the community is still struggling with, in that radiative feedbacks are stronger when the surrounding environment is dry, right? But if we have a shear tropical cyclone, or just in general, there's a chance for that dry environmental air to be imported and to disrupt the storm. And so we're using drop sound observations for in situ thermodynamic measurements, coupled with satellite radiative flux measurements. And now we're hoping to expand this to the new tropics satellite constellation to look at kind of what conditions cause one to beat the other. How do these two processes that are both very important but also kind of contradictory to each other, how do they interplay, how do they overlap, how do they work together or fight, basically? And the very, very last thing is I'm starting to get into tornado world a little bit. I'm not a severe weather expert by any means, but I have a project that I just started off. It's just on a seed grant right now with Kyle Gillette in our department, who predominantly is advised by Kathy Finley at UND. So Kyle kind of worked with me over the summer to get things going for an undergrad student that's taking this over. But this is just a map of where tornadoes take place relative to tropical cyclone centers in a few different coordinate systems. So this is, not a new result by any means. The data's out there. You can find it online. But a question that we're interested in exploring is kind of the front end of the TC tornado forecasting timeline, right? There's a lot of work that's being done on what happens to cells when they cross over land. There's a lot of work that's going on in terms of how extratropical transition affects the distribution of convection and therefore tornadoes. I'm going actually farther back and trying to use the dropson data that I've already been working extensively with over the years to basically say, how far in advance can we find the it factor that a tropical cyclone might have structurally that might cause it to be anomalously tornadic? And the answer might be that it really is just the dry air intrusions and some of the other dynamics that take place at landfall and after landfall that are the most important thing. But we're interested in kind of seeing just how much additional predictability for prolific TC tornado events we can get. Because Hurricane Beryl, for example, and Milton from last year are pretty noteworthy examples of that we still don't have all the answers for. So I actually finished on time, I think, which is rare for me. I'll leave my take-home messages up there, and there's a QR code if you want to contact me through any social media platforms or through my email or anything like that. Happy to take any questions.
Any questions? The ceiling mic is on, so we don't need to pass the mic around.
My first question is, those maps that you show, are those individual cases or are they composite?
Composites. So the number of storms in the composites included in the titles here. So these are all composites. I've done a little bit of work with individual cyclones as well. Honestly, I have more I need to do to really develop robust conclusions. So yeah, everything you saw today was composites.
I have a couple of questions. I'll try to limit them since we're meeting later. First of all, pretty cool stuff. Very nice presentation. Thank you. I was equally excited as you to see like these signatures of asymmetries in the reanalyses. I noticed, and you mentioned this asymmetry in the low-level winds. I'm sorry if I missed it, but do you have an idea why the strongest low-level winds are left of shear?
So this is actually a question that Colin and I have floated around each other a lot. So let me pull up that plot for just.
I've been wondering about this myself.
Yeah. So I think if you just superimpose both the fields and you just do wind speed, it's down shear left.
Mm-hmm.
That is pretty unanimously where you have the strongest just overall wind speed.
Mm-hmm.
There is. I need to spin myself back up on this literature, but I know there's some work in terms of how boundary layer parameterizations affect inflow structures, and specifically the kind of angle of radial inflow that takes place and how realistic that is. I know that's an area of sensitivity here, and I do think that the proportion of, I would need to go back and dig up my all the observational data that I have. But I'm pretty sure that at least in Era 5's case and in some of the climate models I've started to look at, that there is a little bit of the inflow is a little bit overdone relative to the cyclonic component of the flow. We tried to ameliorate that a little bit by looking at what's going on a little bit above the lowest model level. And you do see that signal really start to taper off once you go, at least I mean, there's still anomalous inflow down shear, certainly at 850 millibars, for example, but it's not nearly this pronounced. So that's one, I don't have the answer to that question specifically, but I do think there's some smoke there to further go into, I guess you could say.
Okay. Yeah, after I asked my questions, I remember that there has been some work showing that
I think
maybe.
George Bryan's done a little bit of that.
Yeah, but there has been also some work showing that may be where depending on the storm translation, like that may be related to the storm translation.
I have subtracted the storm translation for all this.
Oh, okay.
But that is also an issue I did run into at a previous moment in my life.
Okay. Can I ask another?
Yeah, I think Chris had a question too.
Oh, sorry.
You can, why don't you go? We
Okay.
have plenty of time, so.
Very quickly about the ventilation in the future climate. Have you looked at the environments, and do you know if the environments are drier or less saturated?
You know, that would be a really elementary thing to examine that I haven't gotten around to yet.
Yeah.
I had this conversation with James earlier. He's interested in kind of similar questions with different model ensembles.
Right.
So it's on my mind already. I want to do that soon. That might be the thing that kind of gets me back into actually coding.
Yeah, you may be familiar with the work, but yeah, there's some work showing that it's counterintuitive, but like water vapor increases with warming, but
Right.
the saturation increases faster, so then you get less saturated environments in the future, which
And
would be
that's kind of the
interesting to
question that I
see.
think is related to like where I'm going with this.
Okay.
So we can talk after
Yeah.
for sure.
Thank you.
You still have a question, Chris?
Yeah. So how do the climate models do on tropical shear? Like, do they simulate it well enough to make their evolution of tropical cyclones in a future scenario plausible?
So that's kind of that's the question I wanted to ask with the very end of this talk. So I don't have the full answer to this yet. I can't confidently tell you that model's good or model's bad. What I will say is that a paper just came out, I forget who lead authored this, but it came out like 2 months ago. And I think this is, not necessarily a new result, but one of the larger sources of uncertainty in future projections of TC frequency, at the very least, is the large scale circulation, is the monthly mean shears that are put out by the models. This plot to me, I mean, yeah, there's certainly differences. There's certainly longer tails in a lot of these different models in terms of how we're distributing the shear that's imparted on an individual cyclone. But I'm at least encouraged by the fact that the observations kind of fall in the middle of this envelope. So my short answer is that I don't have the answer yet. But that's the kind of question that I'm starting to look into with my group in using these larger climate model ensembles. That's kind of like the difference of where my work is, I think, relative to the community, is we're focused on what every cyclone individually is experiencing.
Any other questions?
All right, I'm asking the question coming from the mesoscale meteorology modeling lab.
Yeah.
25 kilometers is your highest resolution.
Yeah.
Pretty much. It's still parameterized convection.
Yep.
Do you expect fundamental change if we run convection with explicit convection?
At 25 kilometers, or are you saying
No,
running a
if you're
global
going
storm
down
result
to
model?
3 kilometers.
It's kind of a scale question, right? Where, I mean, yeah, there are some internal processes that you are simply not able to capture in resolutions like this. Like we're seeing HAFs now explicitly able to capture eyewall replacement cycles. That's great for operational prediction. That's great for short-term storm structure forecasting. Those are things that would be great for forecasting the evolution of an individual cyclone. I'm at least encouraged by just kind of the large scale aspect of all of it, right? Like, I never went into this work necessarily thinking that we were gonna figure out, you know, supercell environments and rain bands like I talked about a couple times. So it's a tough question, honestly, right? Like, I do think there's gonna be value there. And honestly, one of the plots I didn't show is I actually tried to recreate, Rosie, I tried to recreate one of your figures from like your, I think it was your PhD work maybe. And I was trying to do with all the models where it was like a correlation between shear and intensity at different time intervals. It's a mess. So I think in terms of, yeah, like the really, really mesoscale processes, the ventilation, the eye wall replacements, all that kind of stuff. And frankly, also explicitly simulating cloud features and the importance that we know of at cloud, liquid, and ice, and you know how that's simulated. I do think there's going to be more value in that. So of course, I'm loving this transition we're making toward global storm resolving simulations. I think where I kind of approach this is trying to make the most of what we have and seeing if that's really what we need. So hopefully that answers. I feel like I'm giving a lot of non-answers in this Q&A, but it's kind of an exploratory project at this point, so that's why I'm excited to be here.
Maybe as a follow-up to that, on the other end of the resolution question, where do you expect that you might not see, like that's the, you know, the structure that you're seeing with the tilting might break down where the resolution is just too coarse? Because you're up to 1/4 degree, I think.
Yeah.
And you mentioned something like you were even looking at the 1 degree on the other side of the world in the West Pacific to produce anything that was all reasonable?
Yeah, so I mean, the storms yeah, I have all of these kind of, you know, animations for West Pacific composites at a 1 degree grid. And storms are much larger, they're much weaker, all the things you would expect on a 1 degree grid. And I made a joke about this at a conference like 2 years ago, and I was like, there's one pixel that's a little bit more blue than the others. There is still a little bit of evidence of the at least qualitative asymmetry that you would expect, even on a 1 degree grid. The issue with tilt specifically is how I calculate it, because that is itself a very mesoscale feature. Actually had a question from you, I think, at that conference years ago about that. And what we do is essentially calculate a centroid of relative vorticity at various vertical levels, but the way you do that can vary from group to group, from model to model. That's, I mean, center tracking is already enough kind of a pain. So I've explored a few different ways to do that, and frankly, it's just hard to really get anything on a 1 degree grid that really is meaningful. So things like this, yeah, you know, you'll see darker red over here. You'll see more yellow over here, but all the things you would expect to see for a very coarse climate model do still manifest.
All right. So do you mean that if the climate become warmer, we have stronger wind shear?
So that's another question that I'm kind of, the answer to that is very uncertain, I think, at this point. Obviously, there's a lot of, this is not just the tropical cyclone question, right? There's a lot of other sources of uncertainty that come into this for the in terms of large scale circulation. Here, and this is not future climate by any means, so I haven't done this for, because I wanted to mostly compare to observational record, so this is just an overlapping 17-year period where I have, you know, I have SSTs forcing things, and then I also have the observations available to me. At least the historical models are, I would say, more widely variable in the shears that they, you know, simulate around TCs. But I don't know the answer yet in terms of the future climate. I think it's something that, if we just look at, again, monthly mean statistics, it's one of the larger sources of uncertainty out there for TC frequency. So that's something I'd love to do soon, is do this kind of plot, this kind of analysis, but for several different future warming tiers, for example. Seeing, of course, there's concern, right, that maybe there's just a certain threshold of shear for which a seed disturbance never actually forms or anything like that. So there could be some bias that comes into an analysis like this. Or again, something about the intensities of the storms causing more shear because
they themselves are shear disturbances. So there's a lot of questions that opens up, but that is, I guess the answer is it's still kind of a lingering sort of red herring in the field.
All right, well, it's 3 o'clock. Let's thank Jake one more time.